Hey there YouTube, this is SJM4306 back with another video. This one will be a quick one. I recently repaired a coworker's son's Oculus Quest controllers. The joysticks on them, which are actually these guys, started drifting and having problems with tracking and all that. Pretty much all potentiometer based controllers, which is like most of the controllers out there now, will eventually at some point in their life have this problem and require you to replace the joysticks. It's due to just mechanically how joysticks work, like these analog type potentiometer based ones. But I thought it would be interesting to pop this open and see kind of what the cause of that is, and if we can actually see the damage done to this that was causing the drifting. Then I thought that would be pretty interesting, just sort of to get some validation that that's what the actual issue is. So I guess we just start prying. There's a couple tabs that are bent over on the front here that I think we should just be able to kind of unbend. There we go. Okay, now it's pretty much apart. And we can see there's really a couple main components. There's the spring here that keeps downward, or rather, this is upside down, so it would keep upward pressure on the stick, because this stick also has a central push function, and I'll show you what exactly does that portion. So here's a little helical spring that provides sort of the pressure to keep the stick upwards as well as centered. We have the the stick itself here, which has a support axle, which is this little piece here. Let's see if I can get this out. There you go. It's just like a C-shaped piece that keeps the axle centered and sort of right there in that location. There's a metal ring which goes around, and I guess it applies equal pressure or something from this spring centered on the actual ball part of the joystick. And there's two pieces. There's actually more than two pieces. There's two rotating bits, and they're sort of half moon shaped. This one is for the one axis, and it has a little cantilever. Has a tiny little cantilever on the one side that then slides one of the axes up and down. The axes are actually these sliding bars with like the metal contacts. There's sort of this main central part of that attaches a stick to both of those axes, and the other axis is this guy in here. There we go. You can see the shape of that, and the actual metal contact bits are these two. There we go. Get some better lighting here. You can see they slide back and forth in these channels, and they're lubricated. And this is sort of, I don't know what this is made of, but it feels sort of like HDPE, which is like a very kind of self-lubricating type of plastic. And you can see the tiny little fingers that make up the contacts. And just a quick showing, you can see when I move the joystick up and down, it moves only a tiny little bit, that horizontal contact. When I move it left and right, actually I have to put pressure on this ball, you can see the other side moves, and both of them will actually move simultaneously when I move it diagonally. So yeah, that's pretty cool. Okay, on the other side, this is where all the actual circuitry happens. Here's the actual button itself that when you press the stick inwards, this is that click that you feel. And the actual sliding portions, the other end that connects to the slider contacts there, are these black bits. And these are screen printed in like a resistive material. And so as you slide along there, I might have to see if I can grab a microscope or something, show you a better picture of it. But you can kind of see that, hopefully, that there is actually some wear marks that I can see. We're going to grab the microscope in a sec, get you a better view. But yeah, so that's very likely the culprit of the drift. Because if I actually look at this, the metal fingers look fine on here. They don't look worn, they don't look like bent out of place or anything. So yeah, we can actually pull this out too. So yeah, this back bar is literally just for support. But yeah, oh, there you could see. Perfect. Yeah, it's kind of hard. Yeah, if you get at an angle there, you could see it's actually scratched pretty deeply on this side. The other side's fine. So it must have been just one axis. So, I mean, that's what happens. Like if you predominantly use forward and backwards, say, I don't know the orientation of this with respect to the controllers. So this might be left, right, actually. So if that's an action that you perform more often than the other axis, that one's going to get worn faster. I could see a little bit on here. Let me grab a like a digital microscope and point the camera at it and get a better shot, like a really close-up shot of how the wear actually looks. Okay, sorry for the handheld nature of this. It's just kind of how it has to work. Here I have my portable little digital microscope, and I have it zoomed in so you could see here the actual membrane itself. If I go all the way down, here's that tack switch that you could see for the center press. If we move along the track and focus, maybe turn the brightness down a little, sort of to the right level, you see those horizontal striations. They're due to the actual metal fingers on the little cantilever end of the slider actually digging in back and forth, creating kind of like a rut in the road. And so in that portion, yeah, you could see it right there. That's actually worn down, so the resistance actually does change. And these sticks do have like a calibration that you can perform in order to kind of account for variance in like the contact for each axis, but it can only do so much. You can see this side's worn in pretty well too. If we go to the other axis, you could see here the same thing, but just in the other direction. That one you could see really well. So yeah, it's just inevitable. That's the way that these mechanical systems wear in. The fingers are probably fine. The actual metal part, the physical mechanical part's probably fine. It's just this this sort of carbon material, because it has to be made less hard than all the rest of it. It's just inherently less hard, actually. And it just gets worn away just a little bit by little bit every time you use the joystick, every time you wiggle it around. So yeah, that's what happens with these joysticks. Now, luckily, they are starting to make for more and more consoles drop-in Hall effect-based replacements. And the main difference between a Hall effect-based joystick and like a mechanical potentiometer one like this is it uses a magnet and then a stationary chip. And the chip just measures the magnetic field position of the joystick, and then it can use that in order to, output an analog value over the exact same little connector. If we take this over to the side there, this is the actual the pads that connect to the console or to the rest of the controller. And this is all analog, but a Hall chip can actually emulate that. It can actually output like an analog value on the output. So it can be made to work with these kind of joysticks. There's no reason why we still have to be using, potentiometer-based joysticks, other than these are significantly cheaper, but they also have significant shortcomings in terms of like operational life and drift and all that kind of stuff. So anyway, hopefully you guys found this video kind of interesting. Yeah, plenty of other people have done teardowns of analog joysticks. I just thought this would be cool to take a look at. I'm just going to throw this one back together, even though it does drift and it's not great. I'll just keep it in working order and whatever. And if one of my joysticks, maybe the stick breaks or one of the other parts, I could still use this for useful parts. It's just this membrane part is no longer reliable because it has mechanical damage to the carbonized layer. Anyway, hopefully you guys enjoyed this video, and I'll see you in the next one. Bye.